So, whatever we have seen just now, that your that this is A matrix and this dash for transpose, right, such that it can save some space, that is why I have taken transpose, and this is actually B transpose and this is gamma transpose and P is the disturbance, right. So, now look, steady state analysis. First we will see the steady state analysis, that suppose this is your control signal U is 0, uncontrolled mode. When U is 0, uncontrolled mode, and this is your, this part is governor, then turbine, then generator, right. So, and as usual we will see what is the steady state value of delta F, delta Pg, delta Pv, delta E is not our interest, but we will see all these things. And uncontrolled mode, when there is no controller, so U is equal to 0. Now, you know from your control system that when t tends to infinity, where you will get the steady state value, that means S tends to 0. That means system reaches to steady state when S tends to 0 or t tends to infinity, and delta PL is a load disturbance and it is a step input. But if S tends to 0, here there is no question of integral function or integral controller type of thing. So, no question of here in this block diagram k I upon S or something, right, that, but everything is 1 plus STG, 1 plus STT and in this form. Therefore, in this block diagram what you do, you put that S tends to 0. So, make S is equal to 0, then your block diagram will be something like your steady state block diagram. So, if we put, and you will get the same answer whatever you do using final value theorem. So, in this block diagram you put S is equal to 0. That means, if we put it, then this is actually steady state condition. If we put S is equal to 0, this part will be 1, S is equal to 0 here, this part is 1, S is equal to 0 here also, this part is 1, and S is equal to 0 here, this part is Kp, and this is delta Pg, delta PL, but for S is equal to 0 means these are all steady state values. So, that means, this block diagram for S is equal to 0 can be written as, this is delta F S S, this is steady state value, this is to Kp because S is equal to 0 here, right, S tends to 0 means t tends to infinity. Here also it will be delta Pg SS means steady state, and here it is 1, it is 1, it is 1, that means these 3 blocks, here it is 1, here it is 1, here it is 1, for S is equal to 0 you put. So, that means easy way to get the steady state values. So, and this is your delta Fs feedback is here, and U is 0, I am not writing here, but here it is U 0, U is equal to your 0, right. So, that means, from this figure what we will get, it is 1. So, delta PGSS will be delta PVSS and is equal to delta ESS is equal to your minus delta FSS upon R is equal to minus delta FSS upon R, because anyway U is 0, right. So, this is your this is one condition, that delta P, these 3 actually at steady state all these 3 values are equal, that because all are coming 1 1 1. So, this is one equation. So, this is equation 1, right. And similarly, from this block diagram you can write delta FSS is k into Kp into delta PGSS minus delta PL. Even it is a step input, as we have already put that t tends to infinity means S is equal to 0 in this block diagram. In this block diagram, for a step input, do not make it delta PL upon S, right, because already we have put it here. Although it is a step input, that do not put anything, that we will see later when we will use final value theorem. So, question is, so this is delta PGS is this delta minus delta FSS upon R, this is one equation. Another one is delta FSS is equal to Kp into delta PGSS minus delta PL, that is delta FSS is equal to Kp into delta PGSS minus delta PL, right. Now, delta FSS is equal to Kp into the delta PGSS we got, this one is equal to minus delta FSS upon R. So, bracket I have written here delta PGSS is equal to minus delta FSS upon R. So, you put it here, right, minus delta PL, and then Kp is equal to, actually you know that earlier we have seen Kp is equal to 1 upon D. Therefore, this one you make Kp is equal to 1 upon D and you simplify. If you simplify this, you will get delta FSS, the steady state value, is equal to minus delta PL upon D plus 1 upon R. This is equation 2. This is the delta FSS value, right. Next is, so if it is delta FSS, then if you substitute your what you call this delta FSS is here in this expression delta PGSS, the delta FSS is equal to, if you put it here, then you will get expression for steady state expression for delta PGSS, that we will see later, right. So, now you let your what you call the nominal system frequency say 60 hertz, right. Suppose it is 60 hertz. Now, inertia constant say it is h is equal to 5 second. This h inertia in terms of second we have seen in the transient stability analysis for power system analysis course, right. So, assume that load changes by 0.5% for a 1% change in frequency, then we know d is equal to delta PL upon delta F. So, 0.5% upon 1% of F0. So, is equal to 0.5 upon 60, because F0 is 60, F0 is 60, right, 60 hertz, right, and 0.5% 1%, don't making it by 100 or 100, automatically it will be cancel. So, basically it is 0.5 and 1% of your what you call your F0. So, percent cancel, ultimately it will become 0.5 by 60, right. So, that is equal to 1 upon 120 per unit megawatt per hertz, right. That means, d is equal to 1 upon 120. So, Kp is actually reciprocal of d. So, Kp is equal to 120 hertz per unit megawatt. So, Kp value we got. Now, we know that this is also we have seen power system time constant Tp is equal to 2 h upon F0 d. So, h is 5 seconds. So, 2 into 5, right, divided by F0 into d. So, F0 is a 60 hertz and your d is equal to 120, right, 1 upon 120. So, here if you put d is equal to 1 upon 120, that means it will go to the numerator. So, it is basically 2 into 5 into 120 upon 60, that means it is 20 second, right, it is 20 second. So, that means Tp we got, then d value we got, Kp we got, right. Now, assume a speed regulation is 4%, right, that is your R. So, R 4% means it is 4% of the nominal system frequency. So, 4% of F0, that means 4% of 60, that is it is 4 upon 100 into 60. So, 2.4 hertz per unit megawatt, this is R. So, R is equal to 2.40 hertz per unit megawatt. Now, let there is a step load disturbance delta PL is equal to 0.01 per unit megawatt. That is step load disturbance, that is increase. I have written here in the bracket that increase in the disturbance. That means, whenever increase in the disturbance, delta PL you will take as a positive thing, right, positive value. So, 0.01 per unit megawatt. Now, from equation 2 we got this one, delta FSS is equal to minus delta PL upon d plus 1 upon R. So, put all this value, delta PL we have taken 0.01. So, minus 0.01 because of this minus, then d is equal to 1 upon 120 and R is equal to 2.4. So, plus 1 upon 2.4. So, this will become actually minus 0.01 upon 0.425 hertz, but FSS is always delta FSS is always in hertz, right. That means, up to 4 decimal place you take. So, delta FSS will become minus 0.0235 hertz, and if we make it further, so minus 0.0235294 hertz, right. Why I have taken this, I will show you why you have so many decimal places. So, that means steady state value will come actually minus 0.0235 hertz. Now, we know delta PGSS is equal to minus delta FSS upon R. This is from equation 1. This also we know. So, minus and delta FSS is minus of minus 0.0235 upon 2.4. So, delta PGSS will come 0.00979 per unit megawatt, and if you take up to 7 decimal places, a bracket I have made it, it is minus 0.0235294 upon 2.4, it actually comes 0.0098039 per unit megawatt, right, almost same, but I have taken this one. Now, question is, there is a question is we have taken the load disturbance is 0.01 per unit megawatt, but generation at the steady state, that generation should match the load. So, delta PGSS should have become 0.01, but in this case it is coming 0.00979, or other way it is 0.0098. So, slightly less. So, why this is happening? This is happening, I will show you now. This is happening because of your that load is your sensitive to the changes in frequency. So, that is why you are not getting exactly 0.01, because at frequency that it is showing the steady state error, some deviation is there, that minus 0.0235 hertz. That is why this is happening, it is not exactly 0.01, right. So, again from this equation or the block diagram, whatever it is, from this block diagram only we can make it, just hold on. From this block diagram we can write this steady state block diagram, we can write this one, right. This one, from this block diagram we can write delta FSS is equal to Kp into delta PGSS minus delta PL. This is from figure 12b. From this block diagram only we can write, rather than equation 11, directly you can write that this equation, from here it is coming when s tends to 0, right. So, delta FSS is equal to delta PGSS minus delta PL into Kp. This is from the figure 12b, that steady state diagram, right. So, in this case, now if you just see, look at this one, delta FSS. So, delta PGSS minus delta PL is equal to delta FSS minus divided by Kp. So, this is delta PGSS minus delta PL is equal to delta FSS upon Kp, and Kp is equal to 1 upon d. So, Kp is equal to 1 upon d, here I written here. So, that is equal to d into delta FSS. That means that delta PGSS is equal to delta PL plus d into delta FSS. That means delta PL is 0.01 plus this minus 0.0235 upon 120. So, delta PGSS actually coming 0.01 minus this term. That means whatever you got 0.01 minus of this term, right, minus of this term. That means that here it is shown that in here that it is not exactly this one, it is only coming this one, right, up to 7 decimal places. If you take both are same, but I have taken it, this difference is there, and this is this difference, and this difference is happening because of this your, we call sometimes the powers your damping term also d, sometimes we call it, right, because this frequency it is showing some steady state value, it is not exactly 60 hertz, some deviation is there minus 0.0235. So, frequency is not exactly at 60 hertz, it will be f 60 minus 0.0235. Because of this your frequency excursion, that this term is this your delta PGSS will cannot be equal to 0.01, because your your what you call the load is sensitive to the frequency, change in frequency. That is why this difference is there, this is the difference. Now, if d is equal to 0, say if d is equal to 0, I mean load is totally insensitive to the changes in frequency. If d is 0, that means your d is equal to delta PL upon delta F. If that term is 0, that means here d is 0, at that time delta PGSS will become delta PL. So, without any controller, if you try to do this, if there is no controller, frequency after load disturbance, it will show steady state error, and because of the frequency steady state error, delta PGSS cannot meet that load demand. I think it has been, I think this has been your what you call understandable to you. I think you have understood this, right. Now, from equation 2, so we can write delta FSS is equal to minus delta PL upon d plus r. Now, if d is equal to 0, you know delta PGSS is equal to delta PL. Now, in this equation, then what will be the steady state error of frequency? So, if d is 0, it will be basically minus delta PL upon 1 upon r, that is equal to minus r into delta PL, and r is equal to 2.4, therefore, and delta PL is 0.01. So, it will becoming minus 0.024 hertz. That is steady state error actually is what you call, it was earlier it was minus 0.0235, now minus 0.024 hertz, slightly change if d is equal to 0, right. So, from this you have from this you can understand the steady state value of your what you call this one. Similarly, your other steady state values, that whatever you have got, that delta PGSS we have got say 0.00979 or 0.0098 exact one, this is the exact one. That means steady state value for these two things, delta PV and delta E, that delta PV and delta E steady state value, they are same is equal to delta PGS. So, 0.0098. So, not writing here, because in the here I have written here delta PGSS sorry, is equal to delta PVSS is equal to delta ESS. So, all these steady state 3 values are same, right. Therefore, your what you call this thing, that delta Fs there is slight change, so minus 0.0 hertz. Suppose if you there is 4% regulation, if it is a 6% regulation, then it will be on 60 hertz, then this value will change, right. it will become minus 0.036 hertz. So, this and from equation 1, again from equation 1 you will get delta PGSS is equal to minus delta FSS upon R, and from here you are from here we have seen that if D is equal to 0, directly delta PGSS is equal to delta PL you are getting. Now, again from this equation that we have seen that if D is equal to 0, delta FSS is equal to minus R into delta PL, and we know that delta PGSS is equal to minus delta FSS upon R, and that means delta FSS is equal to minus R into delta PL. You substitute here, so R will be cancelled and minus it is plus. So, delta PGSS is equal to delta PL, right. So, that is the idea for this D and without D, right. So, also note I have written here delta ESS is equal to delta PVSS is equal to all will be your equal to 0.01 if is equal to delta PL. All under this case, all this case for D is equal to 0, it will be equal to delta PL, and in this case delta PL value is taken 0.01. So, if load increases delta PL is positive, this should be in your mind, and if load decreases delta PL is negative, right. These two must be in your mind all the time. Now, that means that if load increases, I told you speed decreases, that is frequency decreases, right. So, in our previous analysis just now whatever you have seen that delta PL is 0.01 per unit megawatt, we are not telling just 0.0 per unit, we are telling per unit megawatt, because this is actually related to power, that is why making it 0.01 per unit megawatt, right. Increase of load, frequency deviation is this much, del Fs is equal to minus 0.0235 hertz when load is sensitive to the changes in frequency. Therefore, the system operating frequency will be F will be F0 plus delta Fss, F0 is 60 hertz and delta Fs is minus 0.0235 hertz. So, that means system will operate at 59.97 hertz. I hope you have understood this one, right. So, that is the system operating frequencies. Things are very simple, just you have to keep certain things in mind, a little bit we need to understand, right. Similarly, look, when load decreases, if load decreases, that is 0.01 per unit megawatt, that means delta PL you take minus 0.01 per unit megawatt, because decreases means you have to take negative sign. That means from equation 2 delta FSS is minus delta PL upon D plus 1 upon R. So, it is minus of minus 0.01 divided by 1, D is 1 upon 120 and plus R is 2.4 plus 1 upon 2.4, simplify it will become plus 0.0235 hertz, right. So, F is equal to F0 plus delta FSS. So, it will be 60 and if it is plus, so plus 0.0235, it is 60.0235 hertz, it is just slightly above the nominal system frequency, right. And from equation 1 we know delta PGSS will be minus delta FSS upon R. So, it is minus 0.0235 upon 2.4, because delta FSS is coming plus. So, it will be minus 0.0235 upon 2.4. So, minus 0.0097 per unit megawatt. So, negative sign means that generator will decrease its generation. Suppose it was operating at, for example, say it was operating at 200 megawatts, say, and your 0.01 per unit, say suppose if you make it like this 0.01 per unit megawatt it was there, better you say 1 per unit megawatt, 1 per unit megawatt, and now it load has decreased to 0.01. So, it will be 0.99 per unit megawatt. So, that way your what you call that your system will generate your 10 your this much per unit megawatt power less, right. So, that means generation will decrease, otherwise the negative means the generation will decrease. Suppose 10, for example, if 10 megawatt load decreases, suppose switched off, that means generation also will decrease, right. So, negative sign means generation decrease and positive side for frequency means positive side or what you call that frequency is increasing, deviation is plus, so frequency is increasing, right. So, next is that that is one thing. Now, next is that x dot is equal to x plus bu plus gamma p. We have seen this state your what you call this state space analysis, this all these equations we have seen a, b, gamma, right, and x A is as told you state transition matrix, B is the control transition matrix and gamma is the disturbance transition matrix. So, for uncontrolled system, look, this is all I show how you can obtain, but how you can obtain from this equation also, because all the parameters are known, assuming Tp, Tt, Tr, everything is known, all parameters are known. At the end I will give you those parameters, all the parameters are known. That means u is equal to 0. If u is equal to 0, this term will not be there. Therefore, x dot is equal to a x plus gamma p. Say this is equation I have marked as 17a, right. So, at steady state x is equal to x s s, right. That means all the state variable. For example, just for your understanding, we know that x is equal to x transpose is equal to say x 1, then x 2, then x 3, then x 4, right, x 4. So, if you make it like this, that means my x transpose steady state, that means your x 1 steady state, x 2 steady state, x 3 steady state, and x 4 steady state, right. So, this is transpose. That means that here x is equal to x s means that is your if x s is equal to is this one, that is your x 1 steady state, x 2 steady state, x 3 steady state, and then x 4 steady state values. This is x s s, right. That is what we are taking, that x. So, at steady state x is equal to x s s, right, steady state. That means all the variables are reaching to the steady state value. That means you put x is equal to x s dot here, right, x s here. That means this is a capital X, of course, capital X s s dot is equal to a capital X s s plus gamma p, and capital X s dot is equal to 0, because all the when it reaches the steady state, just hold on, when it reaches to the steady state, suppose there are 4 state variable, it does not matter, when all of them reaches to steady state. For example, take one, for example, something is reaching like this, some steady state values, right, maybe another one reaching to this something, the steady state values, right. When you are reaching to the steady state value, say this is your time and this is your state variable, say some x, right, this is time, right, and when reaching to the steady state, that means there is no change in the current value and the previous difference you take, it will be 0. So, that means all these things reaching to steady state means its derivative is 0, right. For example, if x reaches to a steady state any point, that means its derivative at that point is equal to 0, but if you take somewhere here derivative, if you try to find out the derivative 1. So, approximate definition of derivative is, suppose the current value minus the previous value divided by this your what you call the time span, right. So, but when it reaches to steady state, current value current value and previous value they are same. So, derivative will be 0, right. Therefore, when it reaches all the steady state, the derivatives are 0. So, if it is so, that there should not be any confusion, because you have all the 4 state variables in this case, because you have x 1, x 2, x 3, x 4, all the 4 variables, all are reaching to the steady state, right. At t tends to infinity, it is that is s tends to 0, if t tends to infinity. So, all these things are reaching to steady state, that means all the derivative will become 0. That means x s s dot will be is equal to, basically, just hold on, suppose here I am writing, suppose it is x s s dot actually is equal to your x 1 s s dot, x 2 s s dot, x 3 s s dot, and x 4 your s s dot, and all this dot actually becoming 0, 0, 0, 0, 0, because all are reaching to the steady state. So, that is why here x s dot is equal to 0, right. This you put, that means a x s plus gamma p is equal to 0. That means a x s, a capital X s is equal to minus gamma p, right. That means x s is equal to minus a inverse gamma p, right. That means x s is equal to minus a inverse gamma p. So, that means for our system, when reheat type turbine we have taken, this A matrix actually is a your what you call 4 into 4 matrix, and all these parameters are given here. Kp is equal to 120 hertz per unit megawatt, some we calculated, R is equal to 2.40 hertz per megawatt, that also 4% regulation on 60 hertz. Tp we calculated 20 seconds. Say other parameters are, say Kr is 0.50, Tr is 10 second, say Tt is 0.30 second, and governor time constant 0.08 second, Tt is the steam chase time constant 0.30 second, and the reheat time constant 10 second. All parameters are given. So, in A matrix all the parameters are known. So, you can take the A inverse. Only thing is that for this kind of solution, that A inverse must exist, but for this problem whatever you have taken, that A inverse actually exists. So, that means A inverse means it will be a 4 into 4 matrix, right, A inverse, and multiply by gamma, and disturbance only a single term delta PL. So, in from this x 1 SS, x 2 SS, x 3 SS, x 4 SS, all you will get, it will be a column vector, right, because this is just you multiply, it will become a column vector. So, all you will get it. So, if you have if you all these parameters in MATLAB itself, after writing the A matrix in MATLAB itself, you can verify, and whatever we have done, you will find identical results, right. So, this is one way to find out steady state, this is one way to find out the steady state values. For example, suppose here it is 4 into 4, that is why on the paper we can do it. Suppose this matrix is 50 into 50 or 60 into 60, and suppose A inverse exists, and in that case you will not mathematical on the paper, it is very difficult to find out the steady state values, because you have to do a laborious task. But if A inverse exists, and with all this, if you write the A matrix with just a simple inversion and multiplying all this, you will get all the steady state values, right. So, that is why MATLAB you can verify this, all you take these parameters, because at the steady state actually this TP, all time constant TP, TR, TT, TG, KR, it will have no effect actually. This all these time constant, they have the effect during the dynamic your outcome performance, during the dynamic simulation, right. So, all this time constant, when you take other thing, whatever they have during the transient time, I mean when this transient is there, that all these parameters have effect, but when it reaches to a steady state, so the time constant has no effect at the this thing, right. So, that means whatever value you take, TP, KR, TR, TT, TG, ultimately it will give you the same steady state value whatever you got, but if your Kp and R changes, naturally those steady state value are function of Kp and R. So, that is why if Kp or R changes, steady state value will change. But if you take all the other parameter associated with that S, the Laplace operator, right, you will find they have effect on the transient, but not at the steady state. So, I think this is understandable to you, right. So, this is the your what you call steady state value, and again rewriting from equation 2, right, delta Fs is equal to minus delta PL upon d plus R. Sometimes we define this one as a beta is equal to d plus R, and a beta we sometimes call it is frequency response characteristic, right. So, B is equal to, generally for AGC purpose, B is taken as a beta. It cannot be never less than beta. It is a frequency, sometimes we call it a frequency bias setting. It cannot be beta by less than beta. Those things your what we call, when you take interconnected system, certain things are beyond the scope, but why B should not be taken less than beta? When you will complete this particular topic, at that time I will put this question and ask you, after explaining everything, B should be B is equal to beta, even greater than beta, no problem, but it cannot be less than beta, right. So, this is actually your frequency response characteristic d plus R, and this is your beta. So, because this your what you call that minus delta PL will be beta into delta FSS, right. So, the steady state value also depends on this value d and 1 upon R. If load is sensitive, so changes in frequency, and speed regulation parameter R, that governor speed regulation parameter, plays an important role in terms of your what we call the frequency response. So, this is your what you call, these are the parameters actually I have taken from the literature, standard parameters, these are the standard parameters. So, something like your what you call some responses for uncontrolled mode, right. Non-read type model we will see later, just now it is a your what you call that your thing, that A matrix is a 3 into 3, and for read type, if you suppose in MATLAB Simulink, if you plot this your what you call this frequency response and generation response, you will get like this. We will thank you very much, we will be